Hello, in this video, we will present hydraulic assignment to presentation. Our group member, me, Alvin Jayasun, 07 DKA 23F1029 with Terence Chung Sun Cat, 07 DKA 23F1035. Hydraulic is the branch of science and engineering that study the behavior of liquids, especially water, when they are at rest and in motion. It focuses on how fluid react to force and how this knowledge can be applied to solve real-world engineering problems. So, for the question 1, we need to using many equations to determine the bed slope is required to maintain this discharge under uniform flow condition. Firstly, we must find the area. The formula for area is pi d2 over 8. So pi bracket 1.2 power 2 over 8, and we can get 0.5655 meter square. Next, weighted perimeter. Pi bracket 1.2 over 2, and we can get 1.884 meter. And for hydraulic radius, we use A over P, so 0.5655 over 1.884 equal to 0.300 meter. And then we calculate the slope. 1.8 times 0.013 over 0.5655 times bracket 0.3 power 2 over 3 and power 2, and we get the final answer is 0.0085.
Hi, my name is Terence Strong. Now I would like to present the question 2, which is best hydraulic section refrigerated channel. Okay, first we list out the important information such as n equal to 0.012, width equal to 5 meter, side slope pressure equal to 2 per 3, discharge equal to 10 meter cube per second, last is slope equal to 0.0005. A is require us to calculate the uniform water depth, so we draw out the figure out as the picture. We need to find y that result in a flow of 10 meter cube per second by using the Manning equation for upper channel. So the formula given is Q equal to A times R power of 2 over 3 times slope power of 1 over 2 divided by M. Before insert the data to this formula, we need to find the flow area, which is By plus Zy power of 2, so we will get 5y plus 2 over 3y squared. Next, we need to find R, but before find R, we have to find the P, which is weight parameter. So P formula is equal to B plus 2y squared root 1 plus Z power of 2, then we will get 5 plus 2y square root 1 plus open bracket 2 over 3 close bracket power of 2. Now, we just left R didn't find, so we just insert the formula R equal to A divided by P, this is R. So that now we plug in all the data inside the formula and using calculator to separate it and calculate the part where it has y unknown value answer, and we will get the answer with 5.3666. Since y is unknown, so we use trial and error method by testing different value of y, then computing the corresponding discharge Q. We have tried several numbers to find the y that equal to flow rate of 5.3666 from 1.25, 1.16, 1.05, and so on. The last value we try is 1.07807 and equal to 5.3666. Lastly, we have to put it on the main equation again to verify that how the discharge will be 10. Now we move to the question B. We have to calculate water depth Y for best hydraulic trapezoidal cross-section. So we use the formula B plus 2zy equal to 2y square root 1 plus z power of 2. Then we insert the side slope data, which is 0.67 into z. Then solve the equation and calculate till we get y equal to 4.68.
For question 3, we must calculate the specific energy, critical depth, alternative flow depth, and indicate location of flow is subcritical or supercritical, and the minimum value of specific energy head and critical velocity. First, we must find specific energy. For specific energy, E equal to 1.2 plus bracket 9.52 over 2 bracket 9.81, and we get 5.7999 meter. And then we find critical depth YC. Q equal to YV equal to 1.2 bracket 9.5, and we get 11.4 meter square over S. And we find C equal to 11.4 power 2 over 8.1 power 1 over 3, and we get 2.3662 meter. Next, we calculate the alternative depth. E equal to Y plus 11.42 over 2 bracket 9.81 times Y power negative 2, and we get Y plus 6.6239 Y power negative 2. So we get Y 5.3877 and E is 5.7999. So 5.7999 equal to 5.5877 plus 6.6239 times 5.5877 power negative 2. Next, we must find Fr equal to V over square root GYC equal to 9.5 over square root bracket 9.81 times bracket 1.2, and we can get 2.7688 more than 1. So Fr is more than 1, that means it's supercritical. Next, minimum value of the specific energy head, E min, equal to 3 over 2 Yc. So bracket 3 over 2 times bracket 2.366, we can get 3.5443 meter. And lastly, critical velocity, VE equal to square root G OIC, and we calculate square root bracket 9.81 bracket 2.3662, and we can get 4.8179, and this is specific energy diagram. So since Y lower than YC, the flow is supercritical.
For the last question is hydraulic jump, downstream depth. The data given is width with 3 meter, Q equal to 5.6 meter cube per second, slope is 0.0005, and the n is 0.025. So the formula we're using is Q equal to A times 1 over n times R power of 2 over 3 times slope power of 1 over 2. We know that area is equal to y times 3 and the web perimeter is 2y plus 3. So that R will be 3y over 2y plus 3. We put all the data into the formula and solving it. After solving the calculation, we have to separate it where it has y1 as unknown value and moving the whole number to the right side and calculate them to find the answer. Then we'll get 2.0870. So we know that y1 is unknown. We still use the trial and error method, computing the corresponding discharge Q. After try several values of y, and last we will get 2.2412 meter of y, same with 2.0870 meter cube per second. Next, we have to calculate the YC value, which is equal to cube root Q squared divided by 9.81, and we will get 0.7082 meter. We see that Y value 2.2412 is bigger than the YC, so we can consider it as Y2. After that, we need to find the Y1 by using the formula y2 over 2 open bracket square root 1 plus 8 times 0.1776 square and minus 1 close bracket. Then we will get 0.1335 meter for y1. As you can see, value of y1 0.1335 is smaller than yc 0.7082 meter, so that we can consider it as supercritical flow. Next, for B, we need to find energy loss by using formula EL equal to bracket y2 minus y1 bracket cube divided by 4 times y2 times y1. We put all the data into the formula and we calculate it, and the last we will get the answer with 7.8220. While for C, require us to find power loss. We use the formula P equal to rho GHQ, then we insert the data into the formula, and lastly we will get the answer 429.7 kilowatt. For the last question, find the float number formula with Fr equal to V divided by square root G times D. Before we find the Fr, we have to find the V. So that we use the formula Q equal to AV and insert the data, and lastly we will get the V equal to 13.983 meter per second. So we put the velocity inside the Fr equation and use the calculator to calculate it. Lastly, we will get the answer 12.2187, so that we can consider it is strong jump.
Ethical consideration. In this project, public safety is a key ethical consideration, especially in preventing flood risk and structural failure. Accurate flow calculation help predict hazardous velocities and depth, ensuring the design can handle extreme conditions. Channels are designed with safety margin and sufficient freeboard to avoid overflow, while also guiding the placement of warning system and emergency infrastructure. Additionally, the design work to prevent erosion and protect nearby properties, ensuring long-term safety and stability for the surrounding community.
Next, let's look at the ethical consideration of equitable water resource allocation. This principle focuses on ensuring fair and just access to water for all people, communities, and even ecosystems. Everyone, whether they live upstream or downstream, should have the right to clean and sufficient water. To achieve this, engineers and planners use flow calculation to help balance water supply between upstream and downstream users. This ensures that no single group dominates the resource. By accurately modeling discharge and distribution, we can prevent resource conflicts and promote cooperation among users. Additionally, equitable allocation avoids favoritism in design decisions. It ensures that the needs of underserved or marginalized communities are not overlooked. Ultimately, this approach promotes social justice and inclusive water management, making sure the water resources are shared, responsible, and sustainable among all stakeholders. Last, let's talk about the importance of community involvement in ethical consideration. Community involvement means engaging local stakeholders in the hydraulic design and decision-making process. It ensures that the voice of those directly affected by the project are heard and considered. By involving the community, engineers can better reflect real-world needs in their flow assumption and design choice. This makes the design more practical and effective. It also helps build trust and transparency through a shared understanding of flow models and project goals. Moreover, incorporating local knowledge can improve design relevance and resilience, since local residents often have valuable insight about the environment and water behavior in their area. Last, community involvement leads to more socially responsible and widely accepted infrastructure solutions that benefit everyone. Okay, this is the reference link based on this presentation slide, especially ethical consideration. That's all for our group presentation. Thank you for watching.